Greetings to Ljubljana from Bellevue, Washington. In December 1772, shortly before his 22nd birthday, Ludwig van Beethoven traveled from Bonn to Vienna and began studies with Joseph Haydn. Haydn taught from Gradus ad Parnassum, a classic text published in 1725 which was used by most composers at the time, including Haydn, Mozart, and Beethoven himself, to both study and teach counterpoint. Beethoven kept copies of his exercise with corrections by Haydn, so we have the opportunity to get a small glimpse into their interaction. This page contains 4 exercises in the creation of 4-part first species counterpoint. Haydn has supplied a single melody line for each, marked CF for Canis Firmus, and Beethoven must compose the other 3 lines following the rules of first species counterpoint. We can see in the second exercise that Haydn has corrected the 6th note of the second voice. Here's a transcription, and we can see clearly that in the exercise labeled 146 in the complete works, Haydn has changed the F above middle C to an A. What was the problem? All right, let's take a look at Beethoven's example in modern notation. The top line, marked CF for Canis Firmus, was supplied by Haydn. Beethoven's job was to supply the other 3 melody lines following the rules of first species counterpoint. Let's first take a listen. Certainly no masterpiece, but a solid student effort. So what are the rules that Beethoven had to follow? There are several for first species counterpoint, which is note against note counterpoint, but the most important are those for consonants and for motion. For consonants, the rules are that vertical intervals between notes must be consonant intervals. This includes perfect fifths, octaves, major and minor thirds, and major and minor sixths. The perfect fourth is a bit more problematic in that sometimes it is allowed and sometimes disallowed. It's disallowed in 2-voice counterpoint, but allowed otherwise. So Beethoven easily satisfies the consonant rules by simply making all of his chords triads. So for example, the very first chord is a C major chord, C, E, G, C. He also ends with C appropriately, and the other chords are also triads, as you can check. The motion rules are a little more complex, and the primary rule is that one is not allowed to move into a perfect fifth or a perfect octave via either parallel or similar motion. Similar motion meaning the voices move in the same direction, but by different amounts. So for example, here we have parallel motion between the 6th, and here we have similar motion between a 6th and a 5th. So here in this section, Beethoven has introduced a direct octave, or direct fifth, I'm sorry, between the 6th and the 5th, also called a hidden fifth. And he has another problem in that from the 5th, he moves via similar motion into an octave. So there's a hidden octave here as well. So let's focus just on this part. So perhaps it doesn't sound too bad, but it does violate the rule. And the reason for the rule is that because the 5th and the octaves are the most consonant sounding intervals, this kind of similar or parallel motion tends to hide the independence of the lines. And in counterpoint, one of the goals is to have lines that are very distinct from each other. So Haydn fixes this by changing the F to an A. Let's do that and listen to how it sounds. So a very subtle change, but perhaps an improvement. Here we have contrary motion from the 6th into the now a 3rd, and then we have oblique motion here where one voice stays the same and the other moves into the octave, which is also allowed in first first species counterpoint. Since the rules of counterpoint are fairly well defined, it makes sense that we could try to encode them in a computer program and use that to analyze the music. And of course, we're not the first ones to have thought to have done this, but let's see what we can do. As far as the interface goes, certainly the nicest thing to do would be to be able to select some notes in, say, MuseScore, which is what I'm using here, send them to the program, have it analyze it, and then return the results and display them graphically inside the score. We've made a little bit of effort to try to do this, but it's still pretty difficult and will be safe for future work. For now, we forced you to input the score into the program itself, which is not too terrible, but it does require some extra work. So here we've input the score for the example 146. So, and I'm just looking at the top two lines here for simplicity. So from here to here. And let's look and see what kind of analysis we can do. So it starts off with G above middle C and then C above middle C, which are encoded as G5C6 in C5 is middle C according to the MIDI standard. And we enter all the notes similarly, pretty straightforward. Now let's try analyzing this. We're going to take this set of notes and we're going to apply some first species constraints, which I'll show you later, in the key of C major and see what we get. So, oops. All right, so we get a large series of constraints here. And to make it a little easier to read, there's some pretty printing. So let's take a look at that instead. You can see we have a series of constraints that say that you need to be in the key, which depending on what you care about, you may or may not want to add, but for now we'll put them in. Then there are consonants constraints, which say that each of these intervals has to be one of the consonant intervals. And finally, there are motion constraints, which say that there cannot be parallel or similar motion into a perfect interval. So what we can then do, which again we'll talk about later, is compile these into a lower level language that will be used to determine whether the constraints are satisfied. And I can just show you briefly what that looks like now. So looks pretty ugly, like low-level machine code, but that's more or less what it is. And but now the key thing is that we can take these compiled constraints, evaluate them, and then anything that is not satisfied must be a constraint that is violated. So we filter for those, and we can see which constraints were violated by Beethoven. And again, this is easier to read in a pretty printed form. So let's take a look at that. All right, so what do we have? First of all, we have 3 violations of consonants in that we had perfect fourths in the music that are, and not part of, in this case, second species, two-part first species rules in which a perfect fourth is not allowed. But of course, Beethoven was actually writing 4-part counterpoint, so we can let him get away with this. You can see there's a perfect fourth at the beginning and the end, and then also one at voice 1, beat 8. So if we count 1, 2, 3, 4, 5, 6, 7, 8, we see a fourth over here between the two voices. All right, let's, we can actually soften this rule, which we can do now. We have our first species constraints here, which again I'll explain more later, but one of them is that they have to be in these first species intervals, which didn't include the perfect fourth, but we could also allow the perfect fourth. So we can put that in, go back to our test, reevaluate, and voila, only the motion errors remain. And the errors are between beats 5 and beat 6, and beat 6 and beat 7. We notice that we're going into a perfect fifth in beat 6, and then a perfect octave in beat 7. And sure enough, that corresponds to here, although here it's been fixed, and here. So if this was the original, this was the original error. Let's step back and take a look at an overview of the tool. It was originally written in Haskell, mainly to use the SBV library, a very high quality library for integration with SMT solvers, where SMT stands for Satisfiability Modular Theories. It was soon, however, ported to the Music Tools library in the Agda language, which I'd been developing for some time and which allowed me to use existing work. It was not difficult to integrate with SBV using the Haskell foreign function interface. There are three main layers of abstraction to the tool. The highest level, intended for use by musicians, consists of things like symbolic pitches and intervals, musical constraints, and counterpoint rules. An intermediate layer is also musical but more mathematical, and is the level at which most of Music Tools currently operates. It includes musical abstractions such as pitch and interval, but also, in this case, lower level constraints. And finally, the lowest level consists of a very simple expression language, which can be used both to evaluate constraints and to generate code which satisfies existing constraints with holes using an SMT solver. Let's now look at the code in more detail. We first look at the symbolic module, which contains high-level abstractions intended for use by musicians. So for example, the user can input either D sharp or E flat as a note name. These are enharmonic equivalent and represent the same pitch class, but the user may wish to use one name or the other, and we want to make sure to return in our results the same input name that was used. The primary abstraction here is N pitch or named pitch, which takes a note name and an octave. And notice that there's also an unknown named pitch here, which can be used for synthesis, as will be shown later. Another key abstraction at this level is the named interval, which goes from perfect unison up to perfect twelfth. And if the names provided aren't enough, one can specify an arbitrary interval. The module M constraint contains high-level musical constraints. For example, we have our motion rules for different types of motion. And we have also an interval constraint that says that an interval must lie within an existing set of intervals. And we have a scale constraint that says that a note must be in the scale of a certain musical key. Counterpoint rules are nothing more than a collection of such constraints. For example, for our current first species counterpoint rules, we force that the note must be in the scale of the given key, that intervals must be consonant, and that we disallow similar motion into perfect intervals. High-level constraints are translated to intermediate-level constraints. For example, the interval constraint is translated to a set constraint in the intermediate language. Here, in the set constraint, instead of being expressed in terms of a name pitch, it's expressed in terms simply of an integer. This in turn gets compiled down to the lower level expression language. Similarly, motion constraints at the intermediate level are also compiled down to the low-level expression language. The low-level expression language is very simple, having only two types, integers and booleans. The integers can be either specific values or variables. You can do plus, minus, modulo, if then else. For the booleans, you're allowed basic boolean operators, equalities, and inequalities. There's then a very simple evaluator that can determine whether the expression is true or false or give the integer value. Finally, there's an interface to the SMT solver, which translates the structure into its equivalent Haskell version. And in this case, it compiles down to symbolic integers and symbolic booleans, which can be evaluated by the SMT solver. We can then run the solver and try to solve for any unknown variables. Let's now try synthesis using the SMT solver. As we noted, Beethoven had made an error in his exercise, which was corrected by Haydn, who changed the F5 to an A5. Let's see if we can use the SMT solver to make the same correction. We create a hole where Beethoven's error was, and we now run the tool in synthesis mode. Here we call our solve function using the given input, and we now have to compile this, which I've already done. We then run it. It runs very quickly, and we can look at the result here, and we see that, in fact, it has found the exact same solution that Haydn found. Of course, we cheated a little bit by focusing just on the note that we knew needed to be changed. Although our analysis told us roughly where the error was, it might have required a larger change. So let's actually eliminate all three notes near the error, the note before and after, including the one that Haydn fixed, and see what the solver finds in this case. We again recompile, run the tool, which runs quickly, and take a look at the result. Here I've moved both lines to the same staff to make it easier to see. The three green notes are the ones that were synthesized. We can see that the A was left as is. The previous F was changed to an A, just as Haydn did, but here the original G was changed to a B. Interestingly, this is different than in the paper where the G was changed to an A. There are different weaknesses with each one. Here we have a perfect fourth, which we normally don't want, but there's already other perfect fourths, so we can't really prohibit it. The A in the paper was kind of monotonous, but in any case, this still gives us a reasonable solution as we can listen to. Why don't we try solving the exercise for ourselves, just for one line anyway. We'll leave Beethoven's first and last notes intact and synthesize the rest of them. In order to help make the music more interesting, we added some extra constraints. One thing is we'd like to maximize contrary motion, which helps make the lines more independent. I had already verified that 6 was the best you could do, so we'll set that. And we'll also constrain the number of leaps, which in this case is a motion greater than a major third, to at most 1. This helps the line have more continuity to it. And finally, we'll force all of our notes in the middle to be not allow perfect fourths. So adding these constraints on, we then rerun the program, which I've already recompiled and rerun it. Again, it was very quickly, and we can look at the solution. Again, I've copied everything to one staff to make it easier to read. Interestingly, the solution is again slightly different than in the paper, but it did satisfy our constraints. And I want to say that it would be extremely difficult for a human being to come up with this, especially trying to maximize the contrary motion. But you can see there are indeed 6 instances of contrary motion here. So 1, 2, 3, 4, 5, and 6, and a single leap from this note to this note. Let's take a listen. Better than Beethoven? I'll let you decide. Finally, future work. This is still in early development, so there still may be major changes, but I'm fairly happy with the current abstractions and architecture, and so the next step will be to add more rules, more voices, more species, and try it out on many examples. In particular, I would like to incorporate galant schemata, which were rules used by early to middle period classical composers, including Haydn and Mozart. They're based heavily on counterpoint and would allow one to actually compose music in the classical style. I plan to be at the AGDA Implementers meeting in Edinburgh, Scotland in November, working on this and seeking help from the experts, and would be happy to talk about it or get help there. Thank you very much.